Welcome to my Lab5 report, the falling Slinky. The purpose of my lab is to analyze the falling process of the Slinky. I divided it into two stages. In the stage 1, the upper part of the Slinky is gradually falling while the bottom part remains stationary. I will show it in the following slides. So the system I choose here is the top Slinky, but in the stage 2, the entire compressed Slinky falls to the ground. So the system I choose here is the Slinky as a whole. Because the system that I choose in these two stages are different, so I use Tracker to separately model the two stages and then create a computer model to combine the two motion. This is the Tracker model for the stage 1. The stretched length, which is also the initial position, is 1.6 meters because I choose the bottom part as the origin. The final Y position is actually 0.0453 meters. The time passed is 0.224 seconds. Here's the tracker model for the stage 2. This time, the mass is the total mass of the Slinky, which is roughly 0.2 kilograms. The initial time here, you will see that I plotted 0.224 seconds, which is the time passed in the stage 1 because I want to combine these two stages to build the computer model. The initial Y position here is roughly 0 meters, and the final Y position is minus 0.774 meters. In the stage 1, as you can see, for the top Slinky, there are three forces. The gravitational force and the spring force are all pointing downward, while the drag force is pointing up. For the bottom Slinky, that it is stationary, which is mean that it experiences two equal force, which is the gravitational force and the tension. The tension will be existed even and let go at the top. The Google script model here for the stage 1, the hot fix is actually the bottom point of the Slinky, so I set it at the fixed origin. And the coins of the standard Slinky I searched online is 90. Here I set the initial position, initial velocity, and the mass of the ball. The mass of the ball here is actually mass of the top Slinky. And I set the initial condition to calculate the spring force. In the while loop, I first calculate the net force and then use the Newton's second law to update the velocity and the position and update the spring force. This graph is the result that when I run this code. You will see that the tracker model and the computer model are not perfectly matched with each other. There are some possible reasons. First is that the mass of the top Slinky is actually constantly increasing. And the second is that the B constant of the drag force that I obtained is not by accurate calculation, but I try multiple times to find the fit one. So there might be some errors here. And third is that the mark of the change center of mass based on a small number of frames. This video is very blurry, so the motion change between adjacent frames is very hard to measure. So I skip some frames to measure the motion, the center of the mass, which will make this prediction much more inaccurate. Here is the stage 2. As you can see, the whole Slinky falls down as a whole. It experiences only two forces, the gravitational force pointing down and the drag force pointing up. Here's a glow script for the stage 2. First, the important thing here is initial velocity is calculated by position update formula. In the Y position, it is delta R divided by delta T, which is minus 6.54 meters per second. And I reset the initial time here to 0.225 seconds. In the while loop, I first calculate the net force and then update the velocity and the position of the Slinky. Here is the result that when I run this code, it looks like a straight line, but it's actually a curving line. Not very explicit. And when I compare the tracker model and the computational model, they are matches well with each other, much more better than the stage 1. Here's my conclusion. In the process of my lab, as I much more involved in this lab, I find my lab has a lot of things need to be improved. First is that the raw process of this motion is much more complex. The mass of the top of the slinky, as I say, is experienced an integration process, and the center of the mass of the whole slinky is actually moving down. And the second, the mass, the spring constant, the relaxed length, and the structured length of the slinky are all based on the information online. So, which means that maybe it is not true in this video. And the third is why the raw motion is too fast to capture, the slow motion replay makes the result inaccurate. So it's very hard to shoot a suitable video to analyze in the tracker. But we can reach the general conclusion here is that when you're releasing the stretch the slinky from the top, that will not immediately make the end slinky falls off. Rather, the equilibrium will be broken when the top slinky reaches the end. After that, the whole slinky falls at the hole. Thank you.